Runtime. So going back to our compiler topic, we will because now we have those background knowledge, the basics. We will now get into the runtime. We have finally hammered the user's program into a form that we can execute. The last step is running it. If we compile it to machine code, we simply tell the operating system to load the executable and off it goes. So if compiled, such as changing the source code and then compiling it directly to a machine code, that's the time the machine will run it to that specific hardware. But if you change something in the source code, then it will change as well. So this is directly being controlled by the OS fetching to your hardware. Now, if we compile it to bytecode, we need to start up the virtual machine, which could be written in C, or you can bootstrap it to use your language to run your own VM and load the program into that. In both cases, for all but the basest of low-level languages, we usually need some services that our language provides while the program is running. For example, if the language automatically manages memory, we need a garbage collector going in order to reclaim unused bits. So, aside from those language features or syntax we provided, as well as compiling it and interpreting what that syntax mean and providing the user's errors, at runtime, those are different things because we also need to know or implement code that will allow to reclaim those unused bits. Like in JavaScript, it has a parser. So there is also a way for it to parse. So the parser and the stringify of JavaScript are built into the V8 engine and the Node.js because it has to have some way for you to parse the JSON and then convert it to JSON. While the Web API and the Node.js provides a decode and encode for them to transfer that into a much lower level, which is the UTF-8, and then so that they can transport that into a network through packet. So if our language supports instance of test, so you can see what kind of object you have, then we need some representation to keep track of the type of each object during execution. So this is related to how we track the variables using stock and where they are currently in the environment. What is the value of that object? This is the same concept with this, but we need to be able to make a way for it in runtime. So those are different concept, and we will discuss this moving forward. So all of this stuff is going at runtime. So it's called appropriately the runtime. In a fully compiled language, the code implementing the runtime gets inserted directly into the resulting executable. So with our interpreter, we don't do this. But for compiled language, these compiled language are inserted directly. So there's a separate module such as the .h or .c that we will add in locks, or to be able to implement some context, the visitor pattern, for us to be able to do the context free grammar more efficiently. Using X this, donate this. So in Sego, each compiled application has its own copy of Ghost Runtime directly embedded in it. So whenever you compile an application in Go, the runtime features and module code are already embedded in it. If the language is run inside an interpreter or VM, then the runtime lives there. So if the language is run inside an interpreter or VM, then the runtime lives in the virtual machine, not in the code directly. This is how most of implementation of languages like Java, Python, and JavaScript work. So a JavaScript, it actually inserted by the V8 engine. So that V8 engine inserted that runtime features such as instance of the garbage collector, the so remember the V8 was the one being contacted by the OS in JavaScript. So therefore, that V8 also the one or the node.js when whatever you run your JavaScript or also the one handling the garbage collector just as they are the one handling the queue. Shortcuts and alternate routes, single pass compilers. Some simple compilers interleaving parsing, analysis, and code generation so that they produce output code directly in the parser. Without ever allocating any syntax trees or other intermediate representations. So remember how the virtual machine became an intermediate representation? Some simple compilers actually interleave the parsing and analysis without that step. So they do the code generation directly without this runtime, without this intermediate representation, and without the tree. And it's simple, right? So you have no intermediate data structures to store global information about the program, such as the stack and the heap, and you don't revisit any previously parsed of the code. Therefore, you cannot reuse the part of the code, such as in loops and an if else. That means, as soon as you see some expression, you need to know enough to correctly compile it. So, you don't, create meaning out of those combination of expression or the control flow of the program. So it's a simple compiler, fast compiler, and because it's simple, then you can't do much with it as well. So syntax direct translation is a structured technique for building these all-at-once compilers. You associate an action with each piece of the grammar, usually one that generates output code. Then, whenever the parser matches that chunk of syntax, it executes the action, building up the target code one rule at a time. So it's much easier to write, but can you? The question is, can you do much complex representation with it? The answer is no, of course. Pascal and C were designed around this limitation. At the time, memory was precious that a compiler may not be able to hold an entire source file in memory, much less the whole program. So the variables back then, the static stack, were not be able to be loaded in the memory back then. That's why we have this kind of compiler. This is why Pascal's grammar required type declaration to appear first in a block. So instead of allowing a define first without actually declaring it, sorry. So that is why Pascal requires type declaration to appear first in a block. So in a block, you would have a declaration of the types when writing in Pascal because like you can't like instantiate or create a variable first just like with a normal programming language. It's why in C you can call a function above the code that defines it unless you have an explicit forward declaration that tells the compiler what it needs to know to generate for a call to the later function. So you can call a function above the code that defines it in C, because that will be a complete defined declaration of the function or a variable. And again, remember, function is just a variable. Unless you have explicit forward declaration that tells the compiler what it needs to know to generate code for a call to the later function. Now going back to the virtual machine because it's important. So how does it connect to virtual machine? If your compiler produces bytecode, your work isn't over. That's once that's done. Since there's no chip that speaks that bytecode, it's your job to translate. Again, you have two options. You can write a little mini compiler for each target architecture that converts the bytecode to native code for that machine. You still have to do the work for each chip you support. But this last stage is pretty simple and you get to reuse the rest of the compiler pipeline across all of the machines you support. You're basically using your bytecode as an intermediate representation. Now, the basic principle here is that the farther down the pipeline you push the architecture-specific work, the more of the earlier phases you can share across architecture. There's attention though, many optimization like register allocation and instruction selection work best when they know the strength and capabilities of a specific chip. Figuring out which parts of your compiler can be shared and which should be target specific is an art. So, or you can write a virtual machine, a program that emulates a hypothetical chip supporting your virtual architecture at runtime. So this VM is not really a machine per se or a hardware. It's just a program that emulates a hypothetical chip. And remember, we have two choices. So in this mini compiler, as you can see, we have this one pass, single pass of compiler in each without intermediate representation. Or in virtual machine, which most of the languages has nowadays, including JavaScript, they have this JavaScript, and this JavaScript has two choices. First, they could create a mini compiler or just write a program. So instead of writing a mini compiler for each of those target architecture, you would just write a mini program that emulates a hypothetical chip supporting your virtual architecture at runtime. So running bytecode in a VM is slower than translating it to native code ahead of time, because every instruction must be simulated at runtime each time it executes. So basically, a program will simulate a hypothetical chip. So it will imagine how that chip would respond at runtime. Therefore, there's some work needs to do, and we will discuss that moving forward. So that bytecode will be mapped into a specific chip, but it's not as fast as the ahead of time, which is compiling it to a CPU. But your source code is locked when you compile that, right? So in return, you get simplicity and portability. So implement your VM in say, or implement your program, virtual machine in say C, and you can run your language on any platform that has C compiler. This is how the second interpreter we build in this books works.